One day, our sun will expand into a red giant, growing so huge it could engulf the inner planets, maybe even Earth. But why do stars transform this way, and what happens after? In the next minutes, we'll explore the strange science of red giants, where stellar life turns into cosmic drama. If you enjoy this journey, please like, subscribe, and share. Thank you. Now let's begin. A star begins its life as a dense knot of gas and dust, slowly collapsing under the force of its own gravity. As the cloud contracts, it heats up from within. Deep in the center, temperature and pressure rise until a critical point is reached. Hydrogen atoms, the most common atoms in the universe, begin to fuse. 2 hydrogen nuclei combine to form helium, releasing light and energy. This is the onset of nuclear fusion, the process that powers all main sequence stars. From this point on, a star spends most of its life in this balanced state, known as the main sequence. During this phase, gravity pulling inward is exactly matched by the outward pressure of energy produced through fusion in the core. The result is a stable star that shines steadily for billions of years. The fusion of hydrogen into helium occurs only in the core, the innermost region where temperatures are high enough to sustain such reactions. Outside the core, the rest of the star remains mostly passive, conducting heat outward through radiation and convection. This quiet balance allows stars like the Sun to remain stable for an extended period, typically about 10 billion years in the case of a solar mass star. The energy from the core takes hundreds of thousands of years to travel outward, eventually emerging at the surface as the familiar light of a steady star. From a distance, such a star appears calm and unchanging. But deep inside, this seemingly tranquil object is quietly running out of fuel. Over time, the hydrogen in the core becomes depleted. Helium accumulates in the center, and fusion slows. Without the support of hydrogen fusion to maintain pressure, the core begins to contract. As it shrinks, it heats up. But there is no longer enough hydrogen at the very center to continue fusion there. Instead, a shell of hydrogen surrounding the inert helium core becomes hot enough to ignite. This thin layer now begins to fuse hydrogen into helium, producing new energy. This shift marks the beginning of a transformation. The star leaves the main sequence, slowly evolving into a red giant. Though the core is shrinking, the outer layers respond differently. The energy produced by the new shell of hydrogen fusion begins to exert pressure outward. The star's envelope, its vast outer layers, starts to expand. As the outer layers swell, their temperature drops. The surface cools, shifting the star's color from yellow or white to orange or red. Despite the cooler surface, the star becomes more luminous overall. Its increased size and the energy output from the active shell make it shine more brightly than before. The change in size is vast. A star that once occupied a compact space now swells to many times its original diameter. In the case of the future Sun, it will eventually expand far enough to engulf the inner planets. But that moment lies far ahead in time. For now, the transformation to a red giant proceeds slowly and steadily. Astronomers observe many stars in this phase across the sky. They appear as reddish points of light, cooler in color, but often brighter than main sequence stars. This phase can last for hundreds of millions of years. Though it is shorter than the main sequence lifetime, it is not brief. The internal changes are profound, yet they occur over time spans that dwarf human history. The life of a star is a story of change driven by pressure, heat, and gravity. In the main sequence, hydrogen fusion defines its core activity. As that fuel runs out, new processes take over. The ignition of hydrogen in a shell signals that the core is no longer the engine. Instead, it has become a hot, inert mass of helium, waiting for the next threshold. But the star does not stop. It adjusts, continues, finds a new balance. At this early stage of red giant evolution, the outward appearance belies the inward transformation. The star may appear calm, gently glowing with a soft red hue. But inside, powerful processes are at work. The core grows hotter and denser. The shell of fusion builds new helium that continues to settle into the center. The structure of the star becomes layered, an inert helium core, an active hydrogen shell, and a vast envelope of cooler gas above. This layered structure is essential to understanding how the red giant phase develops. It is not a simple swelling, but a complex and dynamic process. As the helium core contracts, it will one day reach the conditions needed for the next transformation, but at this stage the star is still adjusting to the first shift. It has left the long stability of the main sequence and entered a new period, marked by quiet expansion, increasing brightness, and a deeper red color. The calm appearance of red giants in the night sky invites observation. Through telescopes, astronomers see their broad, diffuse outer layers and study their spectra, which reveal the cooler temperatures of their surfaces. Red giants are not rare. Many stars go through this phase, especially those of low or intermediate mass. They serve as quiet indicators of a star's internal evolution, offering a glimpse into the fate that awaits stars like the Sun. If you are enjoying this quiet journey through the lives of stars, consider liking, subscribing, or sharing this video so others can follow along too. Each red giant is a record of time, a phase in a stellar life that unfolds not in bursts, but in slow expansion, in gentle cooling, in the quiet fusion of layers within. Their story continues in the next step as the core grows hotter still, and new possibilities emerge from deep within. As the hydrogen in the core is depleted and fusion shifts to the surrounding shell, the star becomes increasingly stratified. The contracting core continues to grow hotter, but it remains inert for the time being, composed mostly of helium that does not yet have the conditions required for fusion. Around this core, the hydrogen shell burns steadily, releasing a steady stream of energy that keeps the envelope inflated. This energy is not generated deep at the center as it once was, but now flows from a narrow active layer wrapped around the core like a sleeve of fire. The star's appearance and internal structure continue to evolve under this new balance. The outer envelope of the star, no longer held tightly by the shrinking core, expands dramatically. As it swells, the surface becomes less dense and its temperature drops further. A red giant's surface temperature is relatively cool compared to its previous main sequence phase, often only a few thousand degrees. This gives it the characteristic orange or red color seen through telescopes. Despite the cooler surface, the overall luminosity increases significantly due to the sheer size of the expanded outer layers. The star may become hundreds of times larger in diameter than it was during its main sequence life. This phase is dominated by the persistence of hydrogen fusion in the shell and the continued growth of the helium core beneath it. Over time, helium ash from the shell fusion accumulates and adds to the core's mass. As it grows denser and hotter, the conditions in the core slowly approach a new threshold. For stars with a mass less than about twice that of the Sun, the buildup of helium is a quiet process, but it leads to a sudden and dramatic event known as the helium flash. That moment has not yet arrived in our narrative, but the path toward it is being prepared with every passing million years. The forces within the star are in constant conversation. Gravity presses inward, the heat from shell fusion pushes outward, and the core becomes an increasingly compact reservoir of stored energy. As the core temperature rises, the material within becomes partially degenerate. In this state, pressure is no longer governed solely by temperature, but also by the principles of quantum physics that describe how tightly electrons can be packed. This degenerate matter allows the core to resist further collapse even without undergoing fusion. Yet it continues to heat as helium accumulates. While the core evolves invisibly, the star's outer appearance offers clues. Astronomers measure the color and brightness of red giants and place them on the Hertzsprung-Russell diagram, a graphical tool that shows how stars change over time. Red giants occupy a broad region on this diagram, well above the main sequence and shifted toward cooler temperatures. This placement reflects their large size, high luminosity, and lower surface temperature. In clusters of stars that form together, red giants stand out clearly from their main sequence neighbors. Their location on the diagram confirms their evolutionary stage and helps astronomers estimate the age and mass of the star. The internal structure of a red giant remains layered and dynamic. Above the helium core and the hydrogen-burning shell lies a vast convective envelope. In this region, heat is transported not by radiation, but by rising and falling currents of gas. These motions bring material from deep inside up to the surface and carry cooler material downward. This mixing process has important consequences for the chemical makeup of the star's outer layers. Elements formed during earlier fusion stages, such as carbon and nitrogen, can be dredged up to the surface and become visible in the star's spectrum. This is known as the first dredge-up, and it subtly alters the star's composition and color. The changes occurring in red giants are not violent but steady. Over hundreds of millions of years, the star grows more luminous and more distended. The balance between the burning shell and the inert core determines the pace of evolution. For stars of different initial masses, this phase varies in duration and detail. Lower mass stars evolve more slowly and gently, while higher mass red giants burn more brightly and progress more quickly. Yet all stars within a certain mass range follow the same essential path: core contraction, shell fusion, envelope expansion, and surface cooling. As the hydrogen shell burns and helium continues to build in the core, another effect begins to take place. The temperature in the core rises steadily toward the point where helium fusion becomes possible. But for stars with a mass less than about twice that of the Sun, this transition is not smooth. The core, being made of degenerate helium, behaves differently than ordinary matter. It does not expand in response to heating. Instead, it traps heat, allowing the temperature to climb rapidly. Eventually, a runaway reaction is triggered, igniting helium in a flash. This helium flash, though dramatic internally, is not visible from the outside. It occurs within the compact core and stabilizes the star for its next major phase. That moment lies just ahead. For now, the star remains in the early red giant phase, dominated by hydrogen shell burning and the slow transformation of its internal structure. The outer layers continue to glow softly, cooled by their distance from the core but kept inflated by the steady outward flow of energy. From a great distance, such a star seems peaceful. Its light flickers only slightly, and its surface offers little hint of the complexity within. Yet each photon that escapes carries the quiet story of nuclear processes unfolding in layers too deep to see. Observations of red giants across the galaxy reveal this phase in countless stars. Each is a variation on the same physical principles, shaped by initial mass and composition. Astronomers study their spectra, monitor their oscillations, and compare their positions in the Hertzsprung-Russell diagram. Together, these tools paint a detailed picture of how stars age and change. From this calm, steady light, we learn how matter behaves under extremes of pressure and temperature, and how stars evolve across timescales that stretch far beyond human memory. Each stage prepares the way for the next. In the quiet accumulation of helium, in the soft expansion of the outer layers, in the slow drift toward the helium ignition point, the red giant unfolds its next phase with patience. Soon the core will be ready, and a new kind of fusion will begin. As the helium core continues to grow hotter and denser, the conditions within it gradually approach a critical threshold. This core, composed almost entirely of helium ash from the surrounding shell, is in a peculiar state of matter known as electron degeneracy. In this condition, the particles inside are packed so tightly that their pressure no longer depends on temperature. This is a property unique to degenerate matter, where quantum effects dominate the physics. As heat accumulates, the core does not expand to release it. Instead, the energy builds up quietly, trapped within. The temperature rises with little resistance, and the core remains compact and inert to outward changes. For stars of low to intermediate mass, this quiet build-up leads to an internal event called the helium flash. The helium flash occurs when the temperature at the center of the core reaches a point at which helium nuclei can begin to fuse into carbon. This process requires much higher temperatures than hydrogen fusion, and can only begin once the core has contracted and heated sufficiently. But because the core is degenerate, it does not respond to the onset of fusion by expanding as normal gas would. Instead, the temperature rises rapidly, and fusion proceeds in a runaway fashion. Within a few minutes, an enormous amount of energy is released deep inside the star. However, this burst of energy does not reach the surface. It is absorbed within the surrounding layers and goes into lifting the degeneracy of the core. As the helium flash subsides, the core adjusts. It expands slightly and becomes less degenerate, settling into a new equilibrium. Helium fusion begins in earnest, but now it proceeds in a steady, controlled manner. The star enters a new phase of stability. Helium nuclei fuse to form carbon and oxygen in the core, while hydrogen continues to burn in a surrounding shell. The structure of the star now consists of an active helium-fusing core, a hydrogen-fusing shell, and the extended outer envelope. This balance is less stable than the earlier main sequence phase, but it still lasts for tens or even hundreds of millions of years. During this core helium-burning phase, the star becomes somewhat smaller and less luminous than it was at the peak of its red giant expansion. Its surface may contract slightly and become warmer, though it remains cooler and redder than a main sequence star. In star clusters, red giants in this phase often group together in what is known as the red clump, a tightly packed region on the Hertzsprung-Russell diagram that indicates stable core helium fusion. This stage is particularly useful for astronomers, as it serves as a reliable indicator of stellar evolution and distance. Inside the core, the fusion of helium into carbon and oxygen proceeds gradually. These elements accumulate over time and remain inert once formed, as temperatures in low-mass stars never become high enough to ignite carbon fusion. The ash of this process builds up at the center, creating a new dense core surrounded by active fusion layers. The energy produced continues to support the outer layers of the star, but the structure becomes increasingly complex. Above the helium-burning core lies a shell where helium ash is deposited, and beyond that, the hydrogen-burning shell continues to contribute fresh helium. Each layer plays a role in sustaining the star's energy output. Throughout this period, the star continues to lose mass. Its outer layers are not tightly bound, and can be driven away by the combined effects of radiation pressure and pulsation. Over time, a slow wind carries material outward into space. This mass loss is not violent but steady, a gentle stream of gas and dust that gradually peels away the star's outer envelope. This process becomes more pronounced as the star begins to leave the stable core helium-burning phase and transitions once again into a more unstable state. Eventually, the helium in the core is also exhausted. With no further fuel to fuse in the center, the core contracts once more. Now composed mainly of carbon and oxygen, it becomes degenerate again, shrinking under its own weight. Fusion shifts back to a shell structure, with helium burning in a thin layer around the inert core and hydrogen burning in a shell above that. This dual shell burning leads to a second period of expansion, known as the asymptotic giant branch. The star grows even larger and more luminous than before, with a highly distended envelope and a core that is dense, hot, and composed of fusion byproducts. In this phase, the star becomes more unstable. The fusion shells are thin and delicate, prone to periodic surges known as thermal pulses. These pulses cause the outer layers to expand and contract, and with each episode more material is driven off into space. The convective envelope deepens, dredging up additional carbon and other elements to the surface. These changes give the star a more complex chemical signature and contribute to the enrichment of the surrounding interstellar medium. Some stars even become carbon stars, with more carbon than oxygen in their outer layers, giving rise to distinct molecular bands in their spectra. The star now sheds its mass at an increasing rate. Dust forms in the cooling outer layers and is carried away by stellar winds. These dust-rich shells absorb and re-radiate light, making the star appear dimmer in visible light but brighter in the infrared. Observations of these dusty envelopes provide astronomers with important clues about the late stages of stellar evolution. The material expelled by the star becomes part of the galactic ecosystem, contributing to the formation of new stars, planets, and complex molecules. Through these steps, the star quietly approaches its final transformation. Its core will never be hot enough to fuse carbon, and its mass is not sufficient to collapse further. Instead, it will cast off its outer layers in a last act of dispersal and leave behind only the dense hot core. But for now, in this quiet phase of helium fusion and gentle mass loss, the star continues to shine, continues to change, continues to prepare for the next and final stage. As the star enters the asymptotic giant branch, the changes within become more intricate. The structure now includes a compact inert core composed of carbon and oxygen, surrounded by a shell where helium is fusing into carbon, and beyond that, a second shell where hydrogen is fusing into helium. These layers are extremely thin compared to the size of the star but dominate its energy output. The fusion in these shells is unstable, particularly the helium shell, which undergoes periodic flashes of activity. These are called thermal pulses. Each pulse temporarily increases the energy output, causing the outer layers to expand. After the pulse subsides, the star contracts again. This cyclical swelling and shrinking marks the final active phase of a low to intermediate mass star's life. During these thermal pulses, convection zones temporarily deepen and extend inward. This allows processed material from inside the star to be dredged up toward the surface. This third dredge-up, as it is called, brings carbon and other heavy elements from the interior into the outer envelope. As the star becomes richer in carbon, it may cross a threshold where carbon atoms outnumber oxygen atoms in the atmosphere. In this state, the star becomes a carbon star. Its outer atmosphere forms complex molecules such as carbon monoxide and methane, as well as small dust grains. These give carbon stars their distinctive reddish appearance and infrared brightness. The spectrum of such a star shows unique absorption features that allow astronomers to identify and study them from great distances. As the outer layers continue to expand and cool, dust begins to condense in the star's atmosphere. This dust, composed of carbon compounds, silicates and other materials, plays an important role in the star's later evolution. Carried away by gentle but persistent stellar winds, the dust absorbs visible light and re-emits it in the infrared. This creates an observable shell around the star that grows over time. These expanding dust shells are often spherical or slightly asymmetric, shaped by the dynamics of the stellar wind and rotation. They are rich in the heavy elements formed during the star's life, and contribute significantly to the chemical evolution of the galaxy. The process of mass loss accelerates during the late stages of the asymptotic giant branch. Stellar winds become more intense, and entire layers of the star are carried off into space. Unlike the earlier, slower phase of mass loss, this stage can remove much of the star's outer envelope in a relatively short period of time on stellar timescales, typically a few 100,000 years. The exposed core, no longer shielded by a dense envelope, begins to emerge. At the same time, the ejected gas and dust continue to drift outward, forming a glowing shell that can eventually become a planetary nebula. These planetary nebulae are not related to planets, despite their name. They were given that label centuries ago because they appeared round and planet-like in early telescopes. In reality, they are the extended outer atmospheres of dying stars, ionized by the intense ultraviolet radiation from the hot core now exposed at the center. The core, though no longer undergoing fusion, is still extremely hot and emits energy that lights up the surrounding material. This produces the colorful, glowing structures observed in images taken by modern space telescopes. The shapes of these nebulae vary, from nearly perfect spheres to complex bipolar or elliptical forms, often influenced by magnetic fields, rotation, or the presence of a companion star. The planetary nebula phase is brief, typically lasting only tens of thousands of years. During this time, the nebula expands and fades as the ionizing radiation from the core diminishes. The ejected material mixes with the interstellar medium, adding to the raw materials from which new stars and planets will eventually form. This process of enrichment is one of the most significant legacies of red giants. Through slow, steady fusion and eventual dispersal, they produce and share the carbon, nitrogen, and oxygen that make life possible. The atoms that make up living organisms, the molecules in Earth's atmosphere, and the minerals in its crust all trace their origins to such stars. The core that remains at the center of the nebula continues to cool and contract. It becomes a white dwarf, an object no larger than Earth, but with a mass comparable to that of the Sun. A white dwarf no longer undergoes nuclear fusion. Its light is the fading glow of residual heat. Over billions of years, it will cool further and grow dimmer, eventually becoming a black dwarf, though the universe is not yet old enough for any black dwarfs to exist. The white dwarf is extremely dense, composed of electron-degenerate matter, where atoms are crushed so closely together that a teaspoon of the material would weigh several tons. It does not collapse further because of the pressure arising from the quantum mechanical resistance of electrons being packed into a small space. This pressure, called electron degeneracy pressure, is enough to counteract gravity and support the white dwarf indefinitely. The formation of a white dwarf marks the final state for stars that began with a mass less than about 8 times that of the Sun. These stars avoid the fate of supernova explosions and instead fade gently into cosmic memory. Their quiet endings stand in contrast to the violent deaths of more massive stars. Still, in their calm departure, they have transformed the space around them. The dust and gas expelled during the red giant and planetary nebula phases enrich the galaxy with the building blocks of future generations of stars and planetary systems. The cycle of stellar birth, evolution, and death continues, shaped by processes that unfold slowly, steadily, and without interruption. The white dwarf remains where the star once stood, an enduring remnant of stellar evolution. It no longer fuses elements, yet its gravity and density are extreme. From a great distance it appears as a faint point of light, difficult to detect without sensitive instruments. It no longer illuminates a solar system or sustains any fusion-driven winds. It simply persists, gradually radiating away the heat it once held. In this persistence there is a kind of cosmic silence, a pause in the star's long story, and yet even in this silence the star's legacy continues. Its atoms drift through space. Its light, though fading, may still travel across the galaxy. Its dust may join a cloud where new stars are forming. In these ways, even the quietest endings leave echoes. The journey from main sequence star to red giant to white dwarf is not one of sudden change, but of long transitions, subtle adjustments, and gentle releases of matter and energy into the universe. The distinction between low-mass stars that end their lives as white dwarfs and massive stars that meet more explosive fates lies primarily in mass thresholds and internal temperatures. Stars more massive than about 8 times the mass of the Sun continue evolving beyond the red giant and asymptotic giant branch phases. Their cores become hot enough to fuse carbon, then oxygen, then progressively heavier elements such as neon, magnesium, silicon, and finally iron. Each stage of fusion happens more quickly than the last, lasting from millions of years to mere days. The fusion of iron, however, does not release energy. When iron accumulates in the core of a massive star, fusion can no longer support the pressure of gravity. At that point, collapse becomes inevitable, and the star may end in a core collapse supernova, leaving behind either a neutron star or a black hole. In contrast, the red giant pathway leads not to explosion but to gradual transformation. The energy generation in red giants is never sufficient to push core temperatures past the threshold required for carbon fusion. Instead, the star sheds its outer layers and exposes a carbon-oxygen core that slowly cools as a white dwarf. Despite the quieter ending, the contributions of red giants to cosmic evolution are profound. Their extended lifetimes, widespread presence, and efficient recycling of matter into the interstellar medium make them one of the most significant stellar populations in the galaxy. Astronomers can study red giants in great detail because their physical properties are relatively well understood, and because they are luminous enough to be observed at vast distances. Their spectra reveal the composition of their outer layers, including the products of nuclear synthesis that have been brought to the surface through dredge-up processes. Elements like carbon, nitrogen, and oxygen show distinct absorption lines that can be measured with precision. By analyzing these features, scientists can trace the chemical evolution of stars, star clusters, and entire galaxies. Another powerful tool used to study red giants is astroseismology. This technique examines the subtle pulsations that occur on the surface of stars. These oscillations are caused by waves traveling through the stellar interior, and the way these waves move is influenced by the star's internal structure. In red giants, the interaction between pressure waves and gravity waves provides information about the density, temperature, and composition of the core. By carefully measuring the frequencies and amplitudes of these pulsations, astronomers can reconstruct the internal layers of the star, much like seismologists use earthquakes to study Earth's interior. Astroseismology has revealed surprising details about red giants. For example, it allows astronomers to distinguish between stars burning helium in their cores and those still relying only on shell hydrogen burning. It also provides a way to estimate stellar ages, offering insights into the history of stellar populations in different parts of the galaxy. The oscillations are measured using precise photometric instruments aboard space-based observatories such as the Kepler and TESS missions, which have provided long-term, uninterrupted brightness measurements of thousands of red giants. In addition to internal properties, external characteristics of red giants also provide clues about their evolutionary stage. One such property is luminosity, which increases dramatically as a star expands into a red giant. Coupled with surface temperature, which declines, these properties determine a star's position on the Hertzsprung-Russell diagram. Red giants populate the upper right of this diagram, forming a nearly vertical region called the red giant branch. As the star climbs this branch, its luminosity increases while the surface temperature remains relatively constant. Some red giants, specifically those undergoing stable helium burning in their cores, are found in a region known as the red clump. These stars share similar luminosities and temperatures, making them useful as standard candles for distance measurements. Their predictable brightness allows astronomers to estimate distances to far-off regions of the Milky Way and other galaxies. Observing red clump stars helps refine models of galactic structure and stellar distribution. The red clump itself is a visible reminder of the quiet uniformity found among stars that have entered this stable, if temporary, phase. Metallicity, the abundance of elements heavier than helium, also influences the behavior and appearance of red giants. Stars with higher metallicity tend to lose mass more efficiently due to stronger stellar winds. Metal-rich stars also cool more quickly and may evolve somewhat differently through the red giant phase. Observing these differences across populations allows astronomers to reconstruct the chemical history of galaxies. Older stars, typically lower in metallicity, provide clues about the early universe, while younger, metal-rich stars reveal more recent processes of star formation and supernova enrichment. The presence or absence of companion planets and stars can also shape the evolution of a red giant. As the star expands, it may engulf close-orbiting planets, vaporizing them and altering the angular momentum of the star. In binary systems, mass transfer between stars can lead to complex outcomes, including the formation of unusual objects such as blue stragglers or symbiotic stars. In some cases, the interaction with a companion can shape the planetary nebula that eventually forms, producing bipolar or asymmetric structures instead of the more common spherical shells. Some red giants exhibit long-period variability, changing brightness over weeks or months due to pulsations in their extended atmospheres. These variations are not explosive, but rather rhythmic expansions and contractions of the outer envelope. The most famous of these are mirror variables, named after the star Mirror in the constellation Cetus. These stars show significant changes in brightness over periods of several hundred days, and offer a natural laboratory for studying stellar atmospheres and mass loss. The rhythm of a mirror star reflects its internal structure and the interactions between radiation pressure, gravity, and convection in its outer layers. From these varied observations and tools, a picture emerges of red giants as complex, layered, and dynamic objects. Though they may appear quiet and unchanging from afar, they are in fact sites of deep physical processes where gravity, heat, and time reshape a star from within. They are bridges between generations of stars gathering raw hydrogen and turning it into heavier elements, then sending that material back into space. In this role, they are not only the final stages of stellar life but also the architects of future systems. The story of red giants is not about violence or spectacle, but about scale, slowness, and continuity. Their changes take place over spans of time that stretch far beyond any human framework. Yet through patient observation and steady measurement, astronomers have been able to map their lives with remarkable clarity. From their quiet swelling to their eventual fading, red giants illuminate not only the paths of stars but also the origins of the matter from which planets and life arise. Among the countless red giants scattered across the galaxy, each one tells a variation of the same story. Their paths are shaped not only by mass and composition, but also by time. Stars evolve on timescales far longer than any human civilization. A star may spend billions of years on the main sequence, then transition through the red giant phase over hundreds of millions more. The gradual changes in structure, chemistry, and light output occur so slowly that no shift is perceptible on human timescales, yet over astronomical intervals they are profound. The slowness of these transitions is not a weakness, but a defining characteristic of stellar life. Red giants are slow engines of transformation, and through their deliberate processes the universe is reshaped atom by atom. In open clusters, which are groups of stars that form together from the same molecular cloud, red giants are particularly useful to astronomers. Since all stars in a cluster are roughly the same age, comparing the positions of stars on the Hertzsprung-Russell diagram allows scientists to see how stars of different masses evolve. The point at which stars begin to leave the main sequence and become red giants marks the cluster's turn-off point. The location of this point gives a direct estimate of the cluster's age. As stars ascend the red giant branch, their colour and brightness change in predictable ways, offering a natural clock that tracks stellar lifetimes. In globular clusters, which are older and more densely packed than open clusters, red giants are even more prominent. These clusters often contain tens or hundreds of thousands of stars, many of which have already passed through the main sequence phase. The red giant branch stands out clearly in observations of globular clusters, providing insights into early stellar populations and the chemical evolution of the galaxy. Because these stars are ancient, often more than 10 billion years old, they also offer a glimpse into the conditions of the early universe. Their low metallicity reveals that they formed before supernovae had enriched the interstellar medium with heavier elements. The gradual enrichment of the galaxy over time is due in large part to the quiet work of stars like these. In their interiors, red giants create elements through nucleosynthesis, processes in which atomic nuclei are combined into heavier forms under the pressure and heat of fusion. Hydrogen becomes helium, helium becomes carbon and oxygen, and heavier elements such as nitrogen, fluorine, and neon may be produced in limited quantities. When the outer layers are shed, this enriched material is dispersed into space. It does not travel far at first, but over time, stellar winds and galactic rotations spread these elements throughout the galaxy. They settle into new molecular clouds, mix with unprocessed gas, and contribute to the formation of new stars and planetary systems. The carbon in organic molecules, the oxygen in water, the nitrogen in the atmosphere, all these atoms were once formed in the interiors of red giants or their ancestors. This connection links living systems on planets like Earth to the nuclear processes that unfold over eons in the hearts of distant stars. The life of a red giant may seem remote, but its outcomes are part of the physical fabric of every object composed of matter. The concept that we are made of star stuff is not poetic metaphor but scientific fact, grounded in the measured and predictable outputs of stellar nucleosynthesis and galactic chemistry. As red giants evolve, their influence extends even to the planetary systems they may once have hosted. Planets that once orbited in comfortable zones may find themselves engulfed by the expanding envelope of the star. For the innermost planets, this is a terminal event. The heat and drag from the swollen outer layers of the star can vaporize planetary surfaces and spiral their remnants inward. For planets farther out, the changing radiation from the star may strip atmospheres or disrupt orbital dynamics. Moons may be ejected and asteroid belts disturbed. Even in the absence of direct engulfment, the red giant phase dramatically alters the radiation environment and the gravitational landscape of a planetary system. Our own solar system is not immune to these changes. In approximately 5 billion years, the Sun will exhaust the hydrogen in its core and begin its red giant transformation. Its outer layers will expand beyond the orbit of Mercury and likely engulf Venus and Earth. The fate of Earth depends on complex interactions between tidal forces, mass loss, and orbital evolution. But even if the planet escapes total engulfment, its surface will be rendered uninhabitable by the intense heat and altered solar output. The oceans will boil away, the atmosphere will be stripped, and the surface will be scorched. Long before that, however, life on Earth will have ceased due to the Sun's gradual brightening over time. The red giant phase will be the final act in a solar drama that began more than 4.5 billion years ago. Still, the Sun's transformation into a red giant is not a catastrophic ending, but a natural transition. It will contribute mass to the interstellar medium, enriching future generations of stars with the products of its quiet fusion. The carbon and oxygen it creates will be carried outward, perhaps forming part of a new solar system elsewhere in the galaxy. In this way, the death of a star is never the end of the story. It is a renewal at a broader scale, a handing off of material and energy to the cosmos that sustains the continuous cycle of formation and decay. Some red giants, particularly those nearing the final stages of mass loss, can be observed surrounded by glowing shells of gas and dust. These circumstellar envelopes are rich in molecules and small particles, which interact with light in complex ways. The infrared observations of these systems reveal the fine structure of dust shells, the flow of winds, and the gradual thinning of material as the star prepares to expose its core. These observations offer the closest view of the processes that give rise to planetary nebulae and white dwarfs. In nearby galaxies, where red giants can still be resolved individually, astronomers apply the same techniques to study the history and structure of those systems, using red giants as markers of age and composition. Despite their quiet nature, red giants are among the most visually striking stars in the sky. Many of the brightest stars visible to the naked eye are red giants or supergiants. Their warm, orange-red light and large apparent sizes make them easy to distinguish. Betelgeuse, Aldebaran, and Arcturus are all red giants or stars transitioning into similar phases. They serve as nightly reminders that stars are not static but dynamic and evolving. Observing them is not only an aesthetic experience, but also a glimpse into the life cycles that govern all matter in the universe. The red giant phase is neither brief nor simple. It is a long and intricate chapter in a star's evolution, marked by structural complexity, elemental transformation, and gradual release of enriched material into space. From the outside, red giants may appear serene and still, but within, they are sites of continuous motion and heat, shaping the very atoms that make up the universe. Their presence in the sky is quiet, but their legacy is profound. As the study of red giants deepens, astronomers refine their understanding of how subtle differences in initial conditions lead to variations in their evolution. One such factor is metallicity, the term used to describe the proportion of elements heavier than helium within a star. These heavier elements forged in earlier generations of stars influence how a star forms, how it burns, and how it ends. A star with high metallicity contains more elements such as carbon, oxygen, and iron, and this changes the opacity of its outer layers. Greater opacity affects how energy moves through the star, often making it easier for the outer envelope to expand and for the star to lose mass through stellar winds. Conversely, stars with lower metallicity tend to be more compact and may retain their outer layers for longer periods, slightly altering their behavior as red giants. Observations across the Milky Way and in nearby galaxies show clear differences in red giant populations tied to metallicity. Older populations, like those found in the halo of the galaxy, or in ancient globular clusters, contain stars with low metallicity. These stars reflect the composition of the early universe, formed before multiple generations of supernovae had enriched the interstellar medium. In contrast, younger populations located in the spiral arms of the galaxy are more metal-rich. Comparing these populations gives astronomers a way to trace the chemical evolution of galaxies and to understand how stellar generations build upon one another. The presence and properties of red giants serve as clues to the broader history of the cosmos. Another aspect of red giant behavior that reveals deeper complexity is their variability. While many red giants maintain steady luminosity over long periods, some enter phases of pulsation. These pulsations are the result of instabilities in their extended envelopes, which expand and contract in rhythmic cycles. The physics behind these pulsations involves the interplay between gravity and radiation pressure. When a layer within the star becomes temporarily opaque, it traps heat, expands, then becomes transparent again, releasing that energy. This process creates a cycle of brightness changes that can last from weeks to years. Stars known as long-period variables, including mirror-type stars, are examples of such pulsating red giants. Their brightness can change dramatically over a regular period, making them easily observable even with amateur telescopes. These pulsations also have a direct impact on mass loss. Each expansion phase drives some material away from the star, especially when coupled with radiation pressure on dust grains forming in the atmosphere. Over time, this contributes to the thick shells of gas and dust surrounding older red giants. As more material is expelled, the star becomes increasingly obscured in visible light, but may brighten in the infrared due to the re-radiation of absorbed energy by dust. These changing observational characteristics help astronomers identify and classify red giants in various stages of their evolution. They also provide insight into the final stages before the outer layers are completely detached and the white dwarf core is exposed. The mass loss experienced during the red giant and asymptotic giant branch phases is not uniform. It is shaped by multiple factors including mass, metallicity, pulsation behavior, and the presence of magnetic fields or nearby companions. In some cases, mass loss may proceed in bursts, associated with strong thermal pulses or structural instabilities within the star. In other cases, it may form spiral patterns if a binary companion is present, channeling material in specific directions. Observations from powerful space telescopes such as the Hubble Space Telescope and the James Webb Space Telescope have begun to reveal these complex shapes in great detail. They show that even a relatively gentle process like red giant mass loss can create intricate and beautiful structures in space. When these outer layers become fully detached and begin to drift away from the central star, the process of planetary nebula formation begins. Though the name is historical and unrelated to planets, planetary nebulae represent a critical phase in the life of a red giant. The hot core, now visible and unshielded, emits ultraviolet radiation that ionizes the surrounding gas. This causes the gas to glow, producing the luminous shells seen in many images. These nebulae can take on many shapes, from nearly perfect spheres to elongated or bipolar forms. Their colors arise from the ionization of different elements. Oxygen glows green, nitrogen glows red, and so on, allowing scientists to determine their composition. The expansion of these shells continues for tens of thousands of years before the material disperses into the wider interstellar medium. Eventually, the core cools and contracts into a white dwarf. At this point, all nuclear fusion has ceased. The white dwarf shines only because of the residual heat stored in its dense material. Composed primarily of carbon and oxygen, this core no longer generates energy but resists further collapse due to electron degeneracy pressure. This means that although it continues to cool over billions of years, it remains structurally stable. White dwarfs are extremely dense. A single cubic centimetre may weigh hundreds of kilograms. Their surface gravity is immense, and their structure is unlike anything found in planets or earlier stellar phases. The formation of a white dwarf marks the final chapter in the life of a red giant. Yet the influence of the preceding red giant phase continues long after. The dust and gas expelled by the star form part of the raw material from which future stars and planetary systems emerge. Observations of star-forming regions show that they are rich in elements that could only have come from earlier generations of stars, particularly red giants and supernovae. Without this stellar recycling, the universe would consist almost entirely of hydrogen and helium. The diversity of elements found on Earth and throughout the cosmos exists only because stars like red giants lived, transformed, and quietly returned their matter to space. The cumulative effect of billions of red giants over cosmic time has shaped the galaxy in visible and invisible ways. They enrich the interstellar medium, illuminate the paths of stellar evolution, and provide a window into the past through their light and composition. Even in their silence, white dwarfs continue to mark the positions of ancient stars, reminding astronomers of the continuous cycle that defines stellar life. The rhythm of birth, fusion, expansion, and release plays out endlessly, with each red giant contributing a quiet verse to the larger song of the cosmos. Their light may appear soft, their pace slow, but red giants are among the most consequential objects in the universe. From their interiors come the elements that form life. From their surfaces flow the winds that shape nebulae. From their remains emerge the seeds of new stars. They're not only the conclusion of one story, but the beginning of many others. Through slow change, they prepare the galaxy for what comes next. As the red giant phase unfolds in countless stars across the galaxy, the quiet process of stellar evolution reveals itself not only through light, but also through matter gently returned to space. In their final stages, red giants are surrounded by vast envelopes of gas and dust, slowly drifting outward in expanding shells. These shells, though often invisible to the naked eye, are rich with carbon, oxygen, silicon, and other elements synthesized within the star during fusion. These substances, carried outward by stellar winds and driven by pulsations and radiation pressure, contribute directly to the structure and composition of the interstellar medium. Over time, they mix with other materials in the galaxy, forming new clouds from which stars, planets, and even biological systems may one day emerge. This process of enrichment is not abrupt. The material leaves the star gradually, sometimes over hundreds of thousands of years. With each thermal pulse, a red giant may lose a small fraction of its mass. As these pulses accumulate and as the outer layers expand beyond the gravitational grip of the star, mass loss accelerates. The result is a slow-motion shedding of the star's outer envelope, an act of dispersal rather than destruction. At the center of this expanding cocoon remains the exposed stellar core, now a dense ball of carbon and oxygen, no longer fusing elements but still hot and bright in ultraviolet light. The ultraviolet radiation from this hot core begins to interact with the surrounding gas, ionizing it and causing it to glow. What had been a cool, dark shell of gas and dust becomes a luminous structure, a planetary nebula. These nebulae, though temporary on cosmic scales, can be visible for tens of thousands of years. Their structures vary widely depending on the initial mass of the star, its rotation, magnetic field, and any companions that may have influenced the shape of the expanding envelope. Some are spherical, while others appear as elongated lobes, bipolar shapes, or complex filaments. Each shape tells a story of forces acting gently over time, sculpting matter into intricate forms under the influence of light and motion. As the nebula expands and fades, the central white dwarf cools and dims. No longer capable of fusion, it shines only with the heat it retains from earlier stages. Its light gradually decreases over billions of years. White dwarfs have no fuel to burn, no winds to release, and no further structural change unless they interact with another object. They persist as quiet, dense remnants, marking the final state of stellar evolution for most stars in the universe. Over vast timescales, even white dwarfs will cool enough to become effectively invisible, slowly transitioning into black dwarfs, objects so faint and cold that they no longer emit detectable light. However, the universe is still too young for any black dwarfs to exist today. Though the white dwarf is silent, the effects of the red giant phase linger. The dust and gas expelled during this time carry with them the fingerprints of the processes that occurred within the star. This material is not uniform. It contains tiny grains of silicates and carbon-rich compounds, as well as molecules like carbon monoxide and water vapor. These grains can clump together, forming larger particles and eventually becoming part of solid bodies such as comets, asteroids, or even planets. When astronomers analyze the composition of meteorites or study the atmospheres of exoplanets, they sometimes find isotopic ratios or chemical signatures that point back to red giant stars. In this way, the legacy of a red giant continues long after the light of the star has faded. Its atoms are found in new contexts, in clouds, in rocks, in oceans, in living cells. The slow processes that unfolded over millions of years inside a single star influence matter across the galaxy for billions of years to come. This is the quiet power of stellar evolution. It does not rely on violence or speed, but on steady transformation and release. Every carbon atom in the human body was formed in the heart of a star, most likely one that passed through a red giant phase long before the solar system was born. Our Sun will follow a similar path. In the distant future, when its core hydrogen is exhausted, it will expand into a red giant, shedding its outer layers and forming a planetary nebula. It will not explode or collapse violently, but instead fade gently, leaving behind a white dwarf. The inner planets may be lost, their orbits disrupted, or their bodies consumed by the expanding solar envelope. The outer planets will survive, though altered by changes in solar radiation and gravitational forces. The Sun's mass loss will reshape the orbits of its remaining satellites, scattering some and drawing others inward. For Earth, the red giant phase will be final. Even if the planet is not fully engulfed, the increased heat and radiation will render the surface uninhabitable long before the red giant envelope reaches it. The oceans will boil, the atmosphere will escape into space, and the crust will melt. The end will not be sudden, but it will be complete. Earth will become a scorched remnant orbiting a fading star. Yet the atoms that once formed its atmosphere, its oceans, its living creatures, may be carried away by the solar wind and incorporated into new systems. They may drift for millions of years before settling into a new cloud, perhaps forming part of a different world orbiting a different star. The same process that unfolds in our Sun is mirrored in countless stars across the galaxy. The quiet expansion into red giants, the pulsation and release of outer layers, the formation of glowing shells, and the cooling of white dwarfs, these steps mark the rhythm of stellar life. Each red giant is a phase in this cycle, neither a beginning nor an end, but a point of transition. The materials released by red giants are not waste but inheritance, providing the foundation for future complexity. In this sense, red giants are not only aging stars but also creators of potential. Their existence makes possible the variety and richness of planetary systems, Their slow release of processed elements enables the emergence of chemistry far more complex than hydrogen and helium alone could support. And their remnants, the white dwarfs, serve as cosmic clocks, allowing astronomers to estimate the ages of stellar populations and to trace the history of the universe through cooling curves and population studies. Even the dust they create plays a role. Interstellar dust influences how light travels through space, forming dark bands in spiral galaxies and scattering light to produce the glow of reflection nebulae. This dust acts as a surface for chemical reactions, forming molecules that might otherwise not arise. In the densest regions, dust helps shield clouds from radiation, allowing new stars to form. Without the continuous seeding of dust and elements by red giants, these processes would slow or cease, changing the pace and nature of star formation throughout the galaxy. So the story of red giants is not one of endings but of contribution. Through quiet expansion, through persistent winds, through shells of light and clouds of dust, they shape the future even as they leave the present. Their transformation is measured not in minutes or years, but in epochs. Their effects are recorded not in noise or fire, but in atoms and silence. And long after their light has faded, the universe bears their mark. The presence of red giants within galaxies is not merely a detail of stellar population, but a key component in the broader architecture of cosmic evolution. Their abundance, visibility, and compositional diversity make them excellent traces of galactic structure and history. In spiral galaxies like the Milky Way, red giants are found not only in the spiral arms where star formation is active, but also in the older bulge and halo populations. Their colours and luminosities provide astronomers with tools to map the distribution of stars and to reconstruct the history of stellar birth and aging across galactic environments. When measured carefully, the properties of red giants reveal gradients in metallicity, age, and motion, forming a kind of fossil record embedded in light. Infrared observations are particularly valuable when studying red giants, as their cooler temperatures and dusty envelopes emit strongly in infrared wavelengths. Telescopes such as the Spitzer Space Telescope and the James Webb Space Telescope have extended our reach into distant galaxies by identifying the telltale signatures of red giants. These stars shine clearly in the infrared, even when obscured by dust or distance. By examining the light curves, spectra, and spatial distributions of these stars, astronomers can trace the assembly of galaxies, understand the contributions of mergers, and observe how elements have cycled through generations of stars over cosmic time. Red giants thus serve as luminous markers, linking local observations to universal processes. Beyond galaxies, red giants contribute to the broader environment of galaxy clusters. Their mass loss enriches not only the immediate interstellar medium but also the larger intracluster medium, the diffuse gas that permeates galaxy clusters. Though much of this gas comes from supernovae and massive star winds, the persistent long-term release of material from red giants adds important elements over time. In particular, their contribution to the abundance of lighter elements like carbon and nitrogen is significant. These elements are crucial for forming organic molecules, and their presence in the intracluster medium implies that even in regions far from active star-forming galaxies, the legacy of red giants is present. This wide-reaching influence is made possible by the duration of the red giant phase. Unlike the brief brilliance of supernovae, red giants shine for hundreds of millions of years, often outliving the processes that formed them. They provide a kind of slow background current of enrichment, subtle but steady. Their light travels for thousands or even millions of years before reaching observers on Earth, carrying with it encoded information about their structure, composition, and past. By decoding this light, scientists can reconstruct the internal processes of stars, the age of stellar populations, and even the history of matter itself. One of the most profound discoveries tied to red giants is their role in nuclear synthesis beyond helium. While massive stars and explosive events produce the heaviest elements through rapid fusion and neutron capture, red giants contribute significantly to the formation of elements through the slow neutron capture process, known as the S process. This occurs during thermal pulses in asymptotic giant branch stars, when conditions allow neutrons to be added to atomic nuclei at a slower rate. Over time, this leads to the creation of heavier isotopes such as strontium, barium, and lead. These elements are not as abundant as carbon or oxygen, but they are vital for tracing chemical evolution. Their presence in ancient stars and meteorites confirms that red giants have played a central role in building the periodic table over billions of years. The products of the S process do not remain locked in the star. As mass loss continues, the enriched outer layers are expelled into the interstellar medium, where they mix with gas from other sources. These atoms may then be incorporated into the next generation of stars or planets. In this way, the fingerprints of red giants extend far into the future. They are preserved in stellar atmospheres, planetary crusts, and even in the biological materials of life. The iron in blood, the calcium in bones, and the phosphorus in DNA all trace their origins to fusion processes in ancient stars, many of which pass through the red giant stage. This connection between stellar interiors and living systems is one of the quiet marvels of astrophysics. Studying red giants not only helps scientists understand the life cycles of stars, but also refines the tools used to measure the universe itself. Their brightness and regularity make them useful as standard candles, objects whose luminosity can be predicted from other measurable properties. Red clump stars, in particular, have been employed to estimate distances within the galaxy and to nearby galaxies. By comparing the observed brightness to the expected intrinsic brightness, astronomers can determine how far the light has travelled. These measurements contribute to building the cosmic distance ladder, which in turn supports the measurement of the expansion rate of the universe. In addition to red clump stars, certain types of variable red giants, such as long-period variables and semi-regular variables, offer further tools for measurement. Their periodic changes in brightness can be correlated with their intrinsic luminosity. Though not as precise as other standard candles, their sheer abundance and brightness allow them to be used in contexts where more sensitive tools may not apply. As surveys of the sky grow more comprehensive and precise, red giants continue to serve as anchors in the vast landscape of cosmic distances. The predictability of red giant behavior makes them especially valuable for theoretical modeling. Their internal structures, fusion rates, and mass loss processes can be simulated with increasing accuracy using computational models. These simulations are compared to real observations from space-based and ground-based telescopes. As models improve, they also help refine our understanding of how uncertainties, such as convection, rotation, or magnetic fields, affect stellar evolution. Discrepancies between observed red giant properties and theoretical predictions highlight areas where our knowledge is incomplete, guiding future research. In certain cases, red giants exist in binary systems where interactions between the stars lead to unique evolutionary paths. If a red giant shares a system with a nearby companion, it may begin to transfer mass through gravitational interaction. This can lead to the formation of unusual objects such as cataclysmic variables or symbiotic binaries, where a white dwarf accretes matter from a red giant companion. These systems can produce nova outbursts, enhanced emission lines, or even lead to type Ia supernovae if the white dwarf reaches a critical mass. While these cases are less common, They show that the red giant phase is not always an isolated or quiet process. Under the right conditions, it can drive dramatic phenomena that affect both stars and their surroundings. In the majority of cases, however, red giants evolve alone, without interaction, moving through their phases in solitude. It is this slow, solitary transformation that defines their place in the stellar population. Their legacy is not marked by sudden change, but by slow continuity. Their envelopes expand quietly. Their winds carry atoms softly into space. Their light fades not in a flash, but in a long, lingering glow. In their stillness, red giants reshape galaxies, seed planets, and give rise to life. While the red giant phase is often associated with aging and decline, in the broader context of the universe, it represents a period of active transformation. This phase bridges the gap between the calm efficiency of the main sequence star and the inert finality of the white dwarf. It is a time when internal forces shift dramatically, and the structure of the star becomes increasingly layered and dynamic. Far from being static, a red giant is a system in motion, its interior fusing, its envelope pulsing, and its surface slowly drifting into space. These transformations are not visible in a single night's observation, nor even in a human lifetime, but over astronomical timescales they reshape both the star and the space around it. The outer layers of a red giant are vastly extended compared to its earlier life. In the case of a star like the Sun, this envelope may reach beyond the orbit of Earth. Though this layer is tenuous and diffuse, it dominates the star's visible size. The surface gravity at these outer regions is weak, and material is only loosely bound. As energy from the inner shells pushes outward, gas escapes in a steady wind, creating a slow outflow that moves through the surrounding space. This wind is not violent, but continuous, forming a kind of invisible breeze that carries the star's mass outward. Over time, this flow builds a cocoon of material around the star, enriched with elements created in previous fusion cycles. The temperatures in the outer atmosphere of a red giant are low enough for molecules to form, something not possible in the intense heat of a main sequence star's photosphere. These molecules, such as carbon monoxide, silicon monoxide, and various hydrocarbons, begin to clump together and condense into dust grains. The dust, though microscopic, is highly effective at absorbing and scattering light. Radiation pressure on these grains helps drive the outward flow, accelerating the mass loss. In regions where the dust density is high, light from the star becomes partially obscured, making the object appear redder and dimmer in visible light. In the infrared, however, the star may appear brighter as the dust re-radiates the absorbed energy at longer wavelengths. The resulting dust shells are complex and varied. In single stars, they often form spherical or slightly asymmetric envelopes. In binary systems, the motion of the companion star can twist the outflow into spirals or disks. In some cases, magnetic fields or rotation may also shape the structure of the ejected material. High-resolution imaging has revealed these forms in increasing detail, showing that even the quiet wind of a red giant can leave intricate signatures in the surrounding medium. These structures, while transient, influence how the planetary nebula will later develop, and how the expelled materials mix with the interstellar environment. The cumulative effect of this mass loss is dramatic. Over the course of its red giant and asymptotic giant branch phases, a low or intermediate mass star may shed half or more of its total mass. For the Sun, this means that by the time it becomes a white dwarf, it will have lost much of the mass it carried for billions of years. The remnant left behind, though still massive, will be only a fraction of its former self, compressed into a dense sphere of degenerate matter. This transformation from an expansive, glowing red giant to a compact, dim white dwarf is stark. Yet it is achieved not through explosion but through the slow, persistent release of matter and energy. This process is not without wider consequences. The gravitational balance of any planetary system is tied to the mass of the central star. As the star loses mass, the gravitational pull weakens. Planets that once orbited in stable paths may migrate outward. Moons may escape or shift orbits. The structure of the entire system may become unstable. For stars with close-in planets, the expansion of the red giant envelope may lead to tidal interactions, orbital decay, and eventual engulfment. The energy transferred in this process may cause the planet to spiral into the star's interior, where it is vaporized. In other cases, the engulfment may be incomplete, leaving behind remnants or debris disks that remain detectable long after the star has cooled. In systems where planets survive the red giant phase, they orbit a white dwarf under very different conditions. These remnant systems are of growing interest to astronomers, as they offer a view into the long-term stability of planetary orbits and the potential for planetary bodies to endure extreme stellar evolution. In some cases, rocky debris has been observed accreting onto white dwarfs, providing evidence of asteroid-like objects that survived the red giant phase but were later disturbed into unstable orbits. The presence of metals in the atmospheres of white dwarfs also supports this idea, as these elements should quickly sink below the visible layers unless continuously replenished by infalling material. This delicate aftermath points to the complexity of red giant evolution, not only as a stellar process but as a system-wide transformation. The star changes, but so too does everything in its gravitational and radiative sphere. Dust, planets, comets, and even space itself are affected by the outflow of matter and light. The faint glow of a white dwarf, barely visible among the stars, may mark the final phase of a system that once held multiple planets, swirling winds, and glowing shells of gas. For astronomers, red giants provide a rare opportunity to observe stellar change in action. Because they are so large and luminous, their surfaces can be studied in more detail than those of smaller stars. Some nearby red giants have been imaged directly, revealing surface features such as bright spots, convective cells, and irregular shapes caused by pulsations or mass loss. These observations challenge models and highlight the need for continuous refinement of our understanding. Unlike main sequence stars, whose steady brightness masks much of their internal complexity, red giants show their instability openly. Their variability, asymmetries, and winds are signs of processes that push the limits of hydrostatic equilibrium and radiative balance. Despite this complexity, the overall arc of a red giant's evolution remains predictable. Hydrogen shell fusion leads to core contraction. Helium ignition brings temporary stability. Thermal pulses drive mass loss. The core is exposed. A planetary nebula glows and fades. A white dwarf remains. This sequence, repeated in countless stars, underpins the chemical and structural development of galaxies. It is through these steps that stars return their processed materials to space and make possible the conditions for new stars to form. The seeming simplicity of this story hides the vastness of time and scale it encompasses. From core fusion to dust formation, from planetary engulfment to nebular fluorescence, each step unfolds slowly, patiently, over millions or billions of years. There is no rush, no sudden crescendo, only the unfolding of physical laws across space and time. The star begins as a cloud of hydrogen and ends as a glowing ember. In between, it becomes a red giant, a phase defined not by chaos but by quiet change. It does not rage against its fate. It transforms, expands, releases, and fades, leaving behind the elements from which worlds are made. Among the many aspects of red giant evolution, one of the most delicate and revealing is the relationship between stellar structure and internal sound waves. Though the outer appearance of a red giant may seem serene and unchanging, its interior hums with vibrations, subtle oscillations that resonate through its many layers. These are not audible sounds in the conventional sense, but pressure waves and gravity waves that ripple through the star's dense body. They are caused by convection, fusion reactions, and the physical properties of the layers themselves. By studying these oscillations, astronomers practice the science of astroseismology, a field that allows them to peer into the otherwise hidden interiors of stars. For red giants, these vibrations are particularly informative, as their extended envelopes and layered fusion zones create rich and complex patterns of movement. Using highly sensitive instruments aboard space telescopes, scientists observe tiny variations in a star's brightness over time. These variations, which may be as small as a few parts per million, arise from oscillations at the surface, driven by changes in pressure and density deep within. In red giants, these brightness variations often include multiple overlapping modes, each tied to a different internal process. Some are pressure modes, or P modes, where waves are restored by pressure forces. Others are gravity modes, or G modes, where buoyancy acts as the restoring force. In red giants, mixed modes also appear, waves that behave partly like pressure modes and partly like gravity modes, offering a window into both the outer and inner regions of the star. The analysis of these oscillations provides several key insights. First, it allows astronomers to distinguish between stars that are burning hydrogen in a shell and those that have ignited helium in their cores. These two groups occupy overlapping regions on the Hertzsprung-Russell diagram, making them hard to tell apart through surface observations alone. But their internal structures differ significantly, and this difference affects how sound waves travel. Second, astroseismology can measure the size of the core, the thickness of the fusion shells, and the density gradient between the core and envelope. These measurements inform and refine models of stellar evolution, improving predictions for how stars will age and change. One of the most profound contributions of astroseismology is the ability to estimate stellar age. By comparing the frequencies of oscillation with theoretical models, scientists can determine how far a star has progressed through its red giant phase. This is particularly useful in galactic archaeology, where researchers attempt to reconstruct the formation history of the Milky Way. By measuring the ages of red giants in different parts of the galaxy, astronomers can map the sequence of events that built the galactic disk, bulge, and halo. This age mapping reveals that different regions of the galaxy formed at different times, under different conditions, and that the stars within them retain chemical and structural clues to those origins. Astroseismology also connects red giants to planetary systems. For stars that host exoplanets, seismic analysis provides accurate estimates of stellar radius and mass, which in turn allow for better determination of planet size and orbit. In many cases, planets orbiting red giants are the remnants of systems that once looked similar to our own. As the host star expands and changes, the gravitational balance of the system shifts, and the long-term fates of planets become tied to the complex evolution of their parent star. Observations have confirmed planets orbiting red giants, including some in tight orbits, suggesting they may have migrated inward or survived partial engulfment. These findings offer a glimpse into the future of the solar system, where the inner planets may not endure the Sun's transformation, but some outer planets might. The study of red giants also influences our understanding of the earliest epochs of the universe. By examining very old red giants in the halo of the Milky Way or in nearby dwarf galaxies, astronomers can measure elemental abundances that reflect conditions in the early cosmos. These stars formed from gas that had only been lightly enriched by previous generations. Their low metallicity and specific isotopic ratios help constrain models of the first stars in the early stages of galaxy formation. Red giants thus serve as messengers from a time before Earth formed, carrying within them the chemistry of a young universe still shaping its identity. Not all red giants are created equal. Their individual histories influence their brightness, lifespan, and eventual end states. Some began life with slightly more mass and reached the red giant phase earlier. Others formed in binary systems, where tidal forces and mass transfer altered their development. Some lost angular momentum through magnetic braking. Others spun rapidly and experienced stronger mixing, changing their internal chemistry and surface abundances. Each red giant is a unique outcome of initial mass, composition, and circumstance. Yet they all converge upon similar endpoints: a white dwarf core, a dispersing shell, and a legacy of atoms released into space. The diversity within the red giant population creates a rich tapestry of observational data. Large sky surveys have catalogued hundreds of thousands of red giants, mapping their distribution across the galaxy. These surveys collect information on brightness, colour, variability, and spectrum, creating a detailed census of these stars. When combined with astrometric data from missions like Gaia, which measures positions and motions with extraordinary precision, astronomers can track how red giants move within the galaxy, how they cluster in groups, and how they migrate over time. These movements reflect gravitational interactions, spiral arm dynamics, and the gradual evolution of the Milky Way itself. In studying these stars, scientists are not just watching individual fates unfold, they're reading a grand narrative of change, cooperation, and continuity. The red giant phase, though terminal in one sense, is also transitional. It is the point at which a star becomes most expressive, showing its layered structure, releasing its internal products, and affecting its surroundings more profoundly than at any previous stage. It is a phase of generosity, where the materials forged in the core are returned to the galaxy. This release is neither sudden nor wasteful. It is measured, efficient, and essential. Through their light, their winds, and their remains, red giants shape the cosmos. They are present in every part of the sky, their slow brightness a constant reminder that the universe changes not only through force, but also through patience. Their lives are long, their transformations subtle, and their dwarfs, red giants, conclude their luminous journey, but not their influence. Their fading cores remain embedded in the structure of the galaxy as silent witnesses to a life of transformation and release. The white dwarfs they become are dense, stable, and slow to cool, each one a quiet beacon of a past phase of activity. These remnants drift through space, often alone, sometimes in binary systems, carrying with them the memory of fusion, convection, pulsation, and dispersal. Though no longer visible to the unaided eye, they represent the outcome of a process that spans billions of years. And while they no longer produce energy, their presence affects the gravitational fabric of stellar neighborhoods and the chemical balance of the systems they once influenced. The temperature of a newly formed white dwarf is extremely high, often exceeding 100,000 degrees at the surface. However, without fusion to replenish that heat, it begins to cool steadily over time. This cooling is slow, and for billions of years the white dwarf continues to emit light, first in the ultraviolet and visible parts of the spectrum, then gradually shifting toward the infrared as it fades. The rate of cooling depends on mass, composition, and the thickness of any remaining surface layers of hydrogen or helium. Over immense spans of time, the white dwarf becomes cold and dark. The term for this final state is a black dwarf, though such objects are purely theoretical at present. The universe has not existed long enough for any white dwarf to have cooled completely. Still, the idea of black dwarfs adds one final step to the sequence, a quiet, invisible conclusion to a long and active stellar history. In this final form, the former red giant persists. It no longer shapes its surroundings with light or wind, but it remains an object of immense density and precision. White dwarfs can pack the mass of a star into the volume of Earth. Their surfaces are so compact that a feather would weigh several tons. Gravity at the surface is 100,000 times stronger than on Earth, yet despite this immense force, they are stable. Supported by electron degeneracy pressure, they neither collapse further nor expand. Their matter is arranged at the limit of compression, a strange and fascinating state of physical equilibrium. It is not fusion or heat that holds them up, but the inability of electrons to occupy the same space, a fundamental rule of quantum mechanics expressed on a cosmic scale. In some cases, white dwarfs are not left entirely to their own solitude. If they exist in binary systems with other stars, they may draw material from their companion. This can lead to a variety of outcomes, including novae, where sudden bursts of fusion reignite briefly on the surface, or even type Ia supernovae, when enough mass accumulates for the white dwarf to exceed the Chandrasekhar limit. That threshold, about 1.4 times the mass of the Sun, marks the boundary beyond which electron degeneracy pressure can no longer support the object. The collapse that follows leads to a thermonuclear explosion, completely destroying the star and dispersing its matter into space. These events are rare but bright, visible across galaxies, and serve as crucial tools for measuring cosmic distances due to their consistent peak luminosity. For the vast majority of red giants, however, the end is quieter. No explosion follows. No flash or final flare marks the transition. There is only the fading of light, the gradual cooling of matter, and the continued drift through space. This stillness, far from being uneventful, is full of significance. The mass released during the red giant phase has joined the galactic medium. The atoms forged inside the star have entered circulation. The core that remains is a marker of age and endurance, carrying within its structure the record of temperatures, pressures, and nuclear processes that once defined its life. Even the trajectory of a white dwarf's motion can offer insights. By tracing the paths of thousands of these remnants, astronomers can infer the past motion of their parent stars and the gravitational structure of the galaxy. In this way, white dwarfs continue to inform science long after they have ceased shining brightly. They are data points in the galactic archive, ancient and informative. Their distribution, velocity, and temperature tell a story about the Milky Way's history of star formation, enrichment, and evolution. The story of red giants and their transformation into white dwarfs offers a profound contrast between the visible and the invisible, between activity and silence. While the red giant swells, pulses, and releases its layers into space, the white dwarf contracts, cools, and stabilizes. One phase is expansive and expressive, the other compact and restrained, yet both are essential to the cosmic cycle. One spreads material outward, the other preserves a core inward. One transforms the surrounding environment, the other endures within it. They are two complementary outcomes of the same stellar path, connected by fusion and gravity, separated by the loss of fuel and the shift to degeneracy. This transition is not a failure or collapse in the negative sense, but rather a final adjustment. The red giant has done its work. It has created new elements, released energy for billions of years, and distributed its processed matter into space. The white dwarf is its legacy, a monument to that long labour, preserved in dense, quiet form. Together, the red giant and the white dwarf span the full arc of stellar life for most stars in the universe, including our Sun. This future is written in the physics of fusion, pressure, and time. No action will delay it. No deviation will occur except through the intervention of another object. The Sun will become a red giant. It will expand, shed its outer layers, form a planetary nebula, and leave behind a white dwarf. This sequence is not only likely but inevitable. It is written in the balance of mass and energy, in the life expectancy of hydrogen, in the properties of atomic nuclei. And when it occurs, the Earth, if it still exists, will be altered beyond recognition. Our planet, like so many others, will bear witness to the transition but not survive it. Yet from this transition comes the foundation for new beginnings. The material released by red giants seeds molecular clouds. These clouds collapse under gravity, giving rise to new stars and planetary systems. The elements that once formed one star's body may become the building blocks of future planets, and so, in each red giant's end is the potential for another's beginning. The cycle continues, not because stars choose to die, but because they are bound by the nature of matter, the rules of energy, and the passage of time. The red giant phase, long and luminous, and the white dwarf phase, faint and enduring, are two halves of a stellar legacy. They represent the transformation of mass into light, of fusion into structure, and of isolation into connection. Through them, the galaxy grows, matures, and remembers. Each red giant carries within it the memory of earlier stars and leaves behind the ingredients of future worlds. Its silence, once it fades, is not emptiness but echo. Across the sky, red giants mark their place in the unfolding history of the universe. They shine not with the intensity of young, massive stars, but with a soft, steady light that has endured through time. To the eye they appear calm, warm, and quiet, often standing out among their bluer, hotter counterparts. Yet beneath their glowing surfaces lies a record of change, a story written in fusion, pressure, and persistence. Each red giant carries within it the memory of hydrogen transformed into helium, of internal shells reshaped by heat, and of outer layers slowly drifting into space. These stars are reminders not of decline, but of transition, where matter is rearranged, energy redistributed, and the cycle of stellar life moves forward. In many regions of the sky, red giants appear in great numbers. Globular clusters, for instance, are dense ancient systems where red giants populate the upper right portion of the Hertzsprung-Russell diagram. These clusters, formed billions of years ago, contain some of the oldest stars in the galaxy. Their red giants are low in metallicity, reflecting a time before the galaxy had been enriched by multiple generations of stars. Studying these giants offers a glimpse into the distant past, allowing astronomers to explore the conditions of the early Milky Way. The light from these stars travels for thousands of years before reaching Earth, carrying with it a signal from a time when our planet had not yet formed, and when the building blocks of life were still drifting through interstellar clouds. In younger stellar populations, such as open clusters or spiral arms of galaxies, red giants appear with higher metallicity and greater diversity. Their presence helps astronomers measure the age and evolution of star-forming regions. The colour and brightness of these stars offer precise information about how long ago a cluster began forming stars. Their position on the Hertzsprung-Russell diagram provides insight into the distribution of stellar masses and the progression of stellar evolution. In this way, Red giants serve as both individual witnesses to stellar change and collective indicators of galactic dynamics. Their steady presence forms a kind of scaffolding around which the rest of stellar astronomy is built. Some red giants vary in brightness over time. These variables do not flicker erratically, but instead follow long, regular cycles of expansion and contraction. Their periods may span hundreds of days, during which the star grows slightly larger, then shrinks, then expands again. The physical cause of this pulsation lies in the instability of their outer envelopes. As energy moves outward through the star, it encounters layers that trap heat, become overpressured, and then suddenly release. These changes are subtle in their origin but dramatic in their effect. A red giant may double or triple in brightness over a single pulsation cycle, and then fade again just as gently. Observing these cycles gives astronomers another way to measure the internal structure of the star and to track its evolutionary stage. In a few special cases, red giants exhibit more complex or irregular behavior. These may be stars nearing the end of the asymptotic giant branch, where thermal pulses create episodic bursts of energy and mass loss. Each pulse may trigger a change in the brightness of the star or in the shape of the surrounding envelope. Over time, the combination of pulsation, mass ejection, and radiation pressure sculpts the circumstellar environment into layered shells. In some cases, the expelled material carries traces of earlier pulses, forming concentric arcs visible in infrared or radio wavelengths. These layers preserve a timeline of the star's final centuries or millennia, like tree rings marking each stage of outward change. Though the red giant phase ends with the shedding of the outer envelope, the materials released continue their journey through the galaxy. The dust grains formed in these stellar atmospheres are not inert. They move through interstellar space, occasionally colliding, fragmenting, or sticking together. In denser regions, such as molecular clouds, these grains act as nuclei for the formation of ice mantles and complex molecules. They help shield newborn stars from harsh radiation and assist in the cooling of gas clouds, a necessary step for gravitational collapse. Without the dust provided by red giants, the formation of new stars and planets would proceed more slowly and less efficiently. In this way, each red giant not only ends its own cycle, but contributes to the beginning of others. The influence of red giants also extends to nearby interstellar chemistry. As their winds move outward, they interact with surrounding material, creating shocks and waves that compress and stir the interstellar medium. These interactions can trigger new episodes of star formation or alter the shape of nearby gas clouds. The enriched material also changes the chemical balance of the region, adding carbon, oxygen, nitrogen, and other elements to the interstellar gas. This enrichment affects the composition of future generations of stars, leading to an evolutionary sequence not just in mass and age, but in chemical complexity. From simple hydrogen clouds to stars rich in heavy elements, the pathway is marked at every stage by the quiet work of red giants. In the solar system, the influence of red giants is not limited to the future of the Sun. Meteorites, ancient rocks that preserve the earliest record of solar material, often contain isotopic anomalies that cannot be explained by local processes. These isotopes, rare forms of elements like xenon, neodymium or barium, bear the signature of S-process nucleosynthesis, a process that occurs in red giants. Their presence in solar system material suggests that before the Sun formed, dust grains from ancient red giants had already mixed into the gas cloud that became our system. The fingerprint of those stars is preserved in the oldest solid matter on Earth, linking us to stellar deaths that occurred long before the Sun's birth. This continuity across time is one of the most powerful elements of red giant evolution. The process does not begin and end with a single star, but flows forward. connecting generations of matter and energy. Each red giant is part of a network, contributing to a collective cycle that builds the universe not through abrupt change, but through continuity and release. The atoms that leave the surface of a red giant may journey for millions of years, caught in the spiral arms of the galaxy, before joining a new system. And in that system, they may once again form stars, planets, and perhaps even the chemistry of life. Though the red giant phase is temporary, its contributions are permanent. The structure of galaxies, the chemistry of planetary systems, and the conditions for life all depend on the slow, quiet transformation of stars into giants, and then into remnants. Their silence is not emptiness, but equilibrium. Their stillness is not stagnation, but preparation. Through their patient evolution, they shape the very nature of matter, light, and time. The calm light of a red giant often conceals the profound changes taking place within. To observers on Earth, these stars appear as steady beacons, glowing with a reddish hue and constant brightness. Yet behind that tranquil glow, a complex interplay of physical forces continues to unfold. Inside the star, thin fusion shells operate with increasing intensity, surrounding a core that is contracting ever more tightly. The hydrogen shell adds helium to the core, while the helium shell, when active, fuses into carbon and oxygen. Each of these layers is delicate and precisely balanced. The structure, though enormous in size, is governed by fragile thresholds: temperature, pressure, density, all of which must align exactly for fusion to proceed. As these boundaries are tested and reshaped by time, the star moves ever closer to its final stages. When the thermal pulses intensify, they can begin to alter the pace of mass loss. The outer layers, already loosely bound, become more susceptible to ejection. Every pulse sends shock waves through the envelope, driving matter outward in waves. Over time, this process leads to the gradual peeling away of the star's atmosphere. The transition from red giant to planetary nebula is not a sudden event, but a culmination of repeated cycles of pulse, release, and readjustment. In these last stages, the star becomes enshrouded in dust and gas, veiling its inner core even as that core prepares to emerge. From the outside, the star may appear fainter or more irregular. In the infrared, however, its brilliance remains, as the surrounding dust glows with absorbed and re-emitted light. This dusty shroud contains the elemental record of the star's entire life. Carbon, formed during helium burning, is released in large quantities, along with nitrogen and oxygen from earlier processes. Heavier elements created during S-process nucleosynthesis also join this flow, contributing to the slow chemical transformation of the galaxy. The mass lost by a single red giant is only a small fraction of the galactic total, but when multiplied by the vast number of such stars, the contribution becomes enormous. The enriched material disperses into the interstellar medium, where it mixes with gas from other sources and begins the long journey toward new star formation. This cycle of enrichment, collapse, fusion, and dispersal has operated for billions of years, building the chemical complexity that allows planets, atmospheres, and biology to exist. At the heart of this process is time, deep, slow, uninterrupted time. Unlike short-lived massive stars that end in sudden explosions, red giants take their time, changing slowly, shedding layers over millennia, and finally revealing their cores. This core, once the seat of fusion, is now inert. It no longer supports itself by creating energy, but instead balances through quantum mechanical pressure. Once fully exposed, it becomes the central engine of a planetary nebula. Ultraviolet radiation from the hot core ionizes the surrounding shell, causing it to glow in delicate colors. Hydrogen glows red, oxygen glows green, and other elements add faint traces of blue or violet. These nebulae may persist for tens of thousands of years, slowly expanding and fading as the core cools and the gas disperses. Eventually only the core remains, a white dwarf, with no source of new energy. It cools over billions of years, slowly dimming as it radiates away the last of its stored heat. These remnants are extremely stable and long-lived. A white dwarf can persist for longer than the current age of the universe. Though small in size, it contains the mass of a star. Its gravity is intense, its surface is smooth and uniform, and its light fades so slowly that it becomes an ideal marker of cosmic time. In old star clusters, white dwarfs serve as cooling clocks, allowing astronomers to estimate the cluster's age by measuring the temperature distribution of its remnants. The oldest white dwarfs observed today are about as old as the galaxy itself, providing a lower limit on the age of the Milky Way. Some white dwarfs do not cool in isolation. If located in a binary system, they may interact with a companion star. If the companion is close enough, matter may be transferred from it to the white dwarf's surface. As this material accumulates, it may undergo a sudden thermonuclear reaction, producing a nova. In extreme cases, if the white dwarf gains enough mass to exceed a critical threshold, it may explode entirely in a type Ia supernova. This process is rare among the descendants of red giants, but remains a possibility in systems where stellar companionship alters the standard evolutionary path. Most white dwarfs, however, remain alone, cooling slowly, dimming quietly, and persisting as silent relics of a more luminous past. While individual red giants follow this path in isolation, collectively they shape the character of the universe. Their light fills galaxies with a warm glow. Their dust forms the raw material for future systems. Their remnants become data points in the galactic structure. Without them, the chemical evolution of galaxies would stagnate. Without them, the heavy elements needed for complex chemistry would be rare. In their quiet phases, they serve as laboratories for astrophysics. In their final moments, they illuminate the path to future star formation. Their presence is not only passive but productive, not only luminous but lasting. The understanding of red giants continues to grow. New instruments allow for more precise observations, while theoretical models increase in sophistication. Ongoing sky surveys have identified hundreds of thousands of red giants across the Milky Way, mapping their distribution and properties with unprecedented detail. Missions such as Gaia, Kepler, and TESS have revolutionized astroseismology, allowing astronomers to listen to the internal vibrations of stars and to refine our understanding of their structure. Future observatories will go further, probing deeper into the layers of red giants, resolving their surfaces, and detecting subtle variations in brightness and motion. These efforts are not only about individual stars, but about assembling a coherent picture of stellar life, galactic structure, and cosmic time. In this expanding portrait of the cosmos, red giants occupy a central role. Their lives span billions of years, their changes unfold across centuries, and their effects ripple outward for millennia. Their transitions are not dramatic in the cinematic sense, but they are rich in meaning. They represent balance, patience, and process. Their glow is a quiet announcement of age. Their winds are a gentle dispersal of complexity. Their cores are compressed pages of stellar history, each atom a remnant of high temperature and pressure, now held in place by fundamental forces. In every red giant there is a trace of what came before and a promise of what may come next. Their atoms were drawn from earlier stars. Their light reveals their current structure. Their dust will seed future worlds. The calm redness of their glow is not a signal of fading. but of giving. They give light, they give elements, and ultimately they give the future its form. Long after their names are forgotten, long after their light has dimmed, the imprint of their work will remain. As the narrative of red giants nears its close, the magnitude of their legacy becomes fully apparent. These stars, having begun as modest clouds of hydrogen gas, pass through long epochs of quiet fusion, intricate structural reorganization, and gentle release. In their red giant phase, they expand to immense proportions, cool at the surface, and become visibly transformed, yet their internal processes grow ever more intense. The energy they produce no longer emerges from a stable core as in their main sequence lives, but from burning shells that shift and pulse. Their envelopes become enormous, their winds grow persistent, and their contribution to the galaxy's matter and energy budget deepens with each passing million years. All of this unfolds not in haste but in slow, deliberate cycles, governed by laws that do not rush and cannot be hurried. Red giants are found everywhere in the sky, among old halo stars and metal-poor globular clusters, in the crowded bulges of spiral galaxies, and along the arms of galaxies where newer generations form. Their brightness allows them to be seen across great distances, and their colours set them apart from hotter, younger stars. They stand as visible signposts of stellar aging, marking the locations of intermediate mass stars as they move through their final active stages. In stellar population studies, they reveal patterns of motion, formation, and composition. In cosmology, they serve as distance indicators and tools for measuring galactic structure. Their variability, oscillations, and spectral lines speak volumes about their internal layering and fusion status. In every way, they are deeply informative stars, both beautiful and instructive. Their existence also invites reflection on the future of our own star. Though the Sun today burns steadily on the main sequence, it too will one day evolve into a red giant. This transformation, while billions of years away, is as certain as the laws that govern gravity and nuclear fusion. The Sun's core will eventually run out of hydrogen fuel, shrink and heat, and initiate fusion in surrounding shells. Its outer layers will swell, cool, and redden. Earth, long uninhabitable by that point, may be engulfed, or its orbit may drift outward as the Sun loses mass. The solar system will be reconfigured. Jupiter, Saturn, and their moons may survive in altered orbits, but the Sun will no longer resemble the steady presence it is today. Instead, it will become a luminous red giant, casting its enriched layers into space, forming a planetary nebula, and leaving behind a white dwarf at its centre. This vision of the Sun's transformation is not unique to our system. It echoes across the galaxy and the countless stars that have already passed through these stages. Each red giant now visible is a reminder that stellar change is constant, and that endings are not abrupt terminations but necessary transitions. The matter ejected from red giants is not discarded waste, but the raw material for the next wave of cosmic evolution. The slow shedding of outer layers feeds molecular clouds. The fusion products enrich the medium with carbon, nitrogen, and oxygen. These elements, combined with water ice, silicates, and complex organics, accumulate in the disks of new stars and condense into planets. From these conditions, life can emerge. In this way, red giants are not only stellar phenomena, but essential contributors to the conditions of habitability. The echoes of red giants are also imprinted in the physical matter of our own world. The carbon in organic compounds, the calcium in bones, the oxygen in the atmosphere, the iron in blood. None of these elements originated in the Big Bang. Instead, they were formed in the interiors of stars, released into space through processes like those that unfold in red giants, and gathered into the gas cloud that became the solar system. Every breath, every cell, every grain of sand contains atoms that once cycled through a star. The universe is not composed of lifeless rock and empty vacuum, but of recycled material infused with the past lives of stars. This quiet inheritance, passed from one generation of stars to the next, allows matter to take on new forms, new complexity, and new possibility. In their silence, red giants reveal the strength of process. There is no sudden transformation, no final blaze of drama. Their end is measured, slow, and structured. Their winds rise gently. Their surfaces expand quietly. Their cores contract steadily. Their light dims gradually. Their contribution is not marked by spectacle but by consistency. They show that change does not require noise to be powerful, and that the most profound effects in the cosmos often result from the slow accumulation of energy and time. These stars teach us that the universe builds its complexity not all at once, but step by step, layer by layer, over intervals far beyond human perception. The matter once fused in their interiors will travel outward, joining interstellar clouds, perhaps drawn by gravity into new stars, new systems, and new worlds. The star itself, now a white dwarf, will persist in silence. It will not collapse further, nor reignite. It will cool for billions of years, alone but intact, carrying within it a record of its long and luminous past. This is not death in the ordinary sense, but transformation. A star has not vanished. It has changed state from a fusion-powered body to a remnant of compressed memory. When looking into the night sky, many of the visible stars are red giants. Their gentle light offers a window into stellar maturity, into the slow transformation of energy into structure, and of structure into dispersal. They are the architects of the elements, the engines of enrichment, and the quiet forges from which the materials of life arise. Long after they fade from view, their influence continues, on the galactic medium, on the planets that form from their dust, and on the people who study their light from worlds yet to be.